Foundations of mathematics is the study of the basic mathematical concepts: number, geometrical figure, set, function, and how they form hierarchies of more complex structures and concepts. Especially the fundamentally important structures that form the language of mathematics, formulas, theories, and their models giving a meaning to formulas, definitions, proofs, algorithms, also called metamathematical concepts, with an eye to the philosophical aspects and the unity of mathematics. The search for foundations of mathematics is a central question of the philosophy of mathematics. The abstract nature of mathematical objects presents special philosophical challenges. The foundations of mathematics, as a whole, does not aim to contain the foundations of every mathematical topic. Generally, the foundations of a field of study refers to a more or less systematic analysis of its most basic or fundamental concepts, its conceptual unity, and its natural ordering or hierarchy of concepts, which may help to connect it with the rest of human knowledge. The development, emergence, and clarification of the foundations can come late in the history of the field, and may not be viewed by everyone as its most interesting part. Mathematics always played a special role in scientific thought, serving since ancient times as a model of truth and rigor for rational inquiry, and giving tools, or even a foundation for other sciences, especially physics. Mathematics' many developments towards higher abstractions in the 19th century brought new challenges and paradoxes, urging for a deeper and more systematic examination of the nature and criteria of mathematical truth, as well as a unification of the diverse branches of mathematics into a coherent whole. The systematic search for the foundations of mathematics started at the end of the 19th century, and formed a new mathematical discipline called mathematical logic, with strong links to theoretical computer science. It went through a series of crises with paradoxical results, until the discoveries stabilized during the 20th century as a large and coherent body of mathematical knowledge with several aspects or components: set theory, model theory, proof theory, whose detailed properties and possible variants are still an active research field. Its high level of technical sophistication inspired many philosophers to conjecture that it can serve as a model or pattern for the foundations of other sciences. Historical context: Ancient Greek mathematics. While the practice of mathematics previously developed in other civilizations, the special interests for its theoretical and foundational aspects really started with ancient Greeks. Early Greek philosophers disputed as to which is more basic, arithmetic or geometry. Zeno of Elea, 490 BC ca 430 BC, produced four paradoxes that seem to show that change is impossible. The Pythagorean school of mathematics originally insisted that only natural and rational numbers exist. The discovery of the irrationality of 2, the ratio of the diagonal of a square to its side, around 5th century BC, was a shock to them which they only reluctantly accepted. The discrepancy between rationals and reals was finally resolved by Eudoxus of Cnidus, a student of Plato, who reduced the comparison of irrational ratios to comparisons of multiples, rational ratios, thus anticipating Richard Dedekind's definition of real numbers. In the posterior analytics, Aristotle, 384 BC 322 BC, laid down the axiomatic method to organize a field of knowledge logically by means of primitive concepts, axioms, postulates, definitions, and theorems, taking a majority of his examples from arithmetic and geometry. This method reached its high point with Euclid's Elements, 300 BC, a monumental treatise on geometry structured with very high standards of rigor. Each proposition is justified by a demonstration in the form of chains of syllogisms, though they do not always conform strictly to Aristotelian templates. Aristotle's syllogistic logic, together with the axiomatic method exemplified by Euclid's Elements, are universally recognized as towering scientific achievements of ancient Greece. Platonism as a traditional philosophy of mathematics. Starting from the end of the 19th century, a Platonist view of mathematics became common among practicing mathematicians. The objects of mathematics are abstract and remote from everyday perceptual experience. Geometrical figures are conceived as idealities to be distinguished from effective drawings and shapes of objects. And numbers are not confused with the counting of concrete objects. Their existence and nature present special philosophical challenges. How do mathematical objects differ from their concrete representation? Are they located in their representation, or in our minds, or somewhere else? How can we know them? The ancient Greek philosophers took such questions very seriously. Indeed, many of their general philosophical discussions were carried on with extensive reference to geometry and arithmetic. Plato, 424/423 BC 348/347 BC, insisted that mathematical objects, like other Platonic ideas, forms, or essences, must be perfectly abstract and have a separate, non-material kind of existence, in a world of mathematical objects independent of humans. He believed that the truths about these objects also exist independently of the human mind, but is discovered by humans. In the Meno, Plato's teacher Socrates asserts that it is possible to come to know this truth by a process akin to memory retrieval. Above the gateway to Plato's academy appeared a famous inscription, "Let no one who is ignorant of geometry enter here." In this way Plato indicated his high opinion of geometry. He regarded geometry as the first essential in the training of philosophers because of its abstract character. This philosophy of Platonist mathematical realism is shared by many mathematicians. It can be argued that Platonism somehow comes as a necessary assumption underlying any mathematical work. In this view, the laws of nature and the laws of mathematics have a similar status, and the effectiveness ceases to be unreasonable. Not our axioms, but the very real world of mathematical objects forms the foundation. Aristotle dissected and rejected this view in his Metaphysics. These questions provide much fuel for philosophical analysis and debate. Middle Ages and Renaissance. For over 2,000 years, Euclid's Elements stood as a perfectly solid foundation for mathematics, as its methodology of rational exploration guided mathematicians, philosophers, and scientists well into the 19th century. The Middle Ages saw a dispute over the ontological status of the universals, Platonic ideas. Realism asserted their existence independently of perception, conceptualism asserted their existence within the mind only, nominalism denied either, only seeing universals as names of collections of individual objects. Following older speculations, that they are words, logos. René Descartes published La Géométrie, 1637, aimed to reduce geometry to algebra by means of coordinate systems, giving algebra a more foundational role, while the Greeks embedded arithmetic into geometry by identifying whole numbers with evenly spaced points on a line. It became famous after 1649, and paved the way to infinitesimal calculus. Isaac Newton, 1642-1727, in England, and Leibniz, 1646-1716, in Germany, independently developed the infinitesimal calculus based on heuristic methods greatly efficient, but direly lacking rigorous justifications. Leibniz even went on to explicitly describe infinitesimals as actual infinitely small numbers, close to zero. Leibniz also worked on formal logic, but most of his writings on it remained unpublished until 1903. The Christian philosopher George Berkeley, 1685-1753, in his campaign against the religious implications of Newtonian mechanics, wrote a pamphlet on the lack of rational justifications of infinitesimal calculus. They are neither finite quantities, nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? Then mathematics developed very rapidly and successfully in physical applications, but with little attention to logical foundations. 19th century. In the 19th century, mathematics became increasingly abstract. Concerns about logical gaps and inconsistencies in different fields led to the development of axiomatic systems. Real analysis. Cauchy, 1789–1857, started the project of formulating and proving the theorems of infinitesimal calculus in a rigorous manner, rejecting the heuristic principle of the generality of algebra exploited by earlier authors. In 1821, Cowers analyze, he defines infinitely small quantities as decreasing sequences that converge to zero, which he then used to define continuity. But he did not formalize his notion of convergence. The modern definition of limit and continuous functions was first developed by Bolzano in 1817, but remained relatively unknown. It gives a rigorous foundation of infinitesimal calculus based on the set of real numbers, clearly resolving the Zeno paradoxes and Berkeley's arguments. Mathematicians such as Karl Weierstrass, 1815–1897, discovered pathological functions such as continuous, nowhere differentiable functions. Previous conceptions of a function, as a rule for computation, or a smooth graph, were no longer adequate. Weierstrass began to advocate the arithmetization of analysis, to axiomatize analysis using properties of the natural numbers. In 1858, Dedekind proposed a definition of the real numbers as cuts of rational numbers. This reduction of real numbers and continuous functions in terms of rational numbers, and thus of natural numbers, was later integrated by Cantor in his set theory and axiomatized in terms of second-order arithmetic by Hilbert and Bernays, group theory. For the first time, the limits of mathematics were explored. Niels Henrik Abel, 1802–1829, a Norwegian, and Davari Stegeloy, 1811–1832, a Frenchman, investigated the solutions of various polynomial equations and proved that there is no general algebraic solution to equations of degree greater than 4, Abel-Ruffini theorem. With these concepts, Pierre Wansel, 1837, proved that straight edge and compass alone cannot trisect an arbitrary angle, nor double a cube, nor construct a square equal in area to a given circle. Mathematicians had vainly attempted to solve all of these problems since the time of the ancient Greeks. Abel and Galois works opened the way for the developments of group theory, which would later be used to study symmetry in physics and other fields, and abstract algebra. Concepts of vector spaces emerged from the conception of barycentric coordinates by Mobius in 1827 to the modern definition of vector spaces and linear maps by Peano in 1888. Geometry was no more limited to 3 dimensions. These concepts did not generalize numbers, but combined notions of functions and sets which were not yet formalized, breaking away from familiar mathematical objects. Non-Euclidean geometries. After many failed attempts to derive the parallel postulate from other axioms, the study of the still hypothetical hyperbolic geometry by Johann Heinrich Lambert, 1728–1777, led him to introduce the hyperbolic functions and compute the area of a hyperbolic triangle where the sum of angles is less than 180. Then the Russian mathematician Nikolai Lobachevsky, 1792–1856, established in 1826, and published in 1829, the coherence of this geometry, thus the independence of the parallel postulate, in parallel with the Hungarian mathematician János Ballier, 1800–60, and 1832, and with Gauss. Later in the 19th century, the German mathematician Bernhard Riemann developed elliptic geometry, another non-Euclidean geometry, where no parallel can be found, and the sum of angles in a triangle is more than 180. It was proved consistent by defining point to mean a pair of antipodal points on a fixed sphere and line to mean a great circle on the sphere. At that time, the main method for proving the consistency of a set of axioms was to provide a model for it. Projective geometry. One of the traps in a deductive system is circular reasoning. A problem that seemed to befall projective geometry until it was resolved by Carl von Staudt. As explained by Laptev and Rosenfeld, 1996. In the mid-19th century, there was an acrimonious controversy between the proponents of synthetic and analytic methods in projective geometry, the two sides accusing each other of mixing projective and metric concepts. Indeed, the basic concept that is applied in the synthetic presentation of projective geometry, the cross ratio of 4 points of a line, was introduced through consideration of the lengths of intervals. The purely geometric approach of von Staudt was based on the complete quadrilateral to express the relation of projective harmonic conjugates. Then he created a means of expressing the familiar numeric properties with his algebra of throws. English language versions of this process of deducing the properties of a field can be found in either the book by Oswald Veblen and John Young, Projective Geometry, 1938, or more recently in John Stilwell's Four Pillars of Geometry, 2005. Stilwell writes on page 120. Projective geometry is simpler than algebra in a certain sense because we use only 5 geometric axioms to derive the 9 field axioms. The algebra of throws is commonly seen as a feature of cross ratios since students ordinarily rely upon numbers without worry about their basis. However, cross ratio calculations use metric features of geometry, features not admitted by purists. For instance, in 1961 Coxeter wrote Introduction to Geometry without mention of cross ratio, Boolean Algebra and Logic. Attempts of formal treatment of mathematics had started with Leibniz and Lambert, 1728-1777, and continued with works by algebraists such as George Peacock, 1791-1858. Systematic mathematical treatments of logic came with the British mathematician George Boole, 1847, who devised an algebra that soon evolved into what is now called Boolean algebra, in which the only numbers were 0 and 1 and logical combinations, conjunction, disjunction, implication, and negation, are operations similar to the addition and multiplication of integers. Also De Morgan publishes his Laws, 1847. Logic becomes a branch of mathematics. Boolean algebra is the starting point of mathematical logic and has important applications in computer science. Charles Sanders Peirce built upon the work of Boole to develop a logical system for relations and quantifiers, which he published in several papers from 1870 to 1885. The German mathematician Gottlob Frege, 1848-1925, presented an independent development of logic with quantifiers in his Begriffsschrift, Formula Language, published in 1879, a work generally considered as marking a turning point in the history of logic. He exposed deficiencies in Aristotle's logic and pointed out the 3 expected properties of a mathematical theory: consistency, impossibility to prove contradictory statements. Completeness. Any statement is either provable or refutable, i.e. its negation is provable. Decidability. There is a decision procedure to test any statement in the theory. He then showed in Grundgesetze der Arithmetic, basic laws of arithmetic, how arithmetic could be formalized in his new logic. Frege's work was popularized by Bertrand Russell near the turn of the century. But Frege's two-dimensional notation had no success. Popular notations were X for universal and X for existential quantifiers, coming from Giuseppe Peano and William Ernest Johnson, until the symbol was introduced by Genson in 1935 and became canonical in the 1960s. From 1890 to 1905, Ernst Schroeder published Vorlesungen über die Algebra der Logik in 3 volumes. This work summarized and extended the work of Boole, De Morgan, and Peirce, and was a comprehensive reference to symbolic logic as it was understood at the end of the 19th century. Peano arithmetic. The formalization of arithmetic, the theory of natural numbers, as an axiomatic theory, started with Peirce in 1881 and continued with Richard Dedekind and Giuseppe Peano in 1888. This was still a second-order axiomatization, expressing induction in terms of arbitrary subsets, thus with an implicit use of set theory, as concerns for expressing theories in first-order logic were not yet understood. In Dedekind's work, this approach appears as completely characterizing natural numbers, and providing recursive definitions of addition and multiplication from the successor function, and mathematical induction. Foundational crisis. The foundational crisis of mathematics, in German, Grundlegende Krise der Mathematik, was the early 20th century's term for the search for proper foundations of mathematics. Several schools of the philosophy of mathematics ran into difficulties one after the other in the 20th century, as the assumption that mathematics had any foundation that could be consistently stated within mathematics itself was heavily challenged by the discovery of various paradoxes, such as Russell's paradox. The name paradox should not be confused with contradiction. A contradiction in a formal theory is a formal proof of an absurdity inside the theory, such as 2 + 2 = 5, showing that this theory is inconsistent and must be rejected. But a paradox may either refer to a surprising but true result in a given formal theory, or to an informal argument leading to a contradiction, so that a candidate theory, where a formalization of the argument might be attempted, must disallow at least one of its steps. In this case, the problem is to find a satisfying theory without contradiction. Both meanings may apply, if the formalized version of the argument forms the proof of a surprising truth. For instance, Russell's paradox may be expressed as there is no set of all sets except in some marginal axiomatic set theories. Various schools of thought on the right approach to the foundations of mathematics were fiercely opposing each other. The leading school was that of the formalist approach, of which David Hilbert was the foremost proponent, culminating in what is known as Hilbert's program, which thought to ground mathematics on a small basis of a logical system proved sound by metamathematical finitistic means. The main opponent was the intuitionist school, led by L.E.J. Brouwer, which resolutely discarded formalism as a meaningless game with symbols. Van Dalen, 2008. The fight was acrimonious. In 1920, Hilbert succeeded in having Brouwer, whom he considered a threat to mathematics, removed from the editorial board of Mathematische, the leading mathematical journal of the time. Philosophical views. At the beginning of the 20th century, three schools of philosophy of mathematics were opposing each other: formalism, intuitionism, and logicism. Formalism. Mathematics. It has been claimed that formalists, such as David Hilbert, 1862–1943, hold that mathematics is only a language and a series of games. Indeed, he used the words formula game in his 1927 response to L.E.J. Brouwer's criticisms. And to what has the formula game thus made possible been successful? This formula game enables us to express the entire thought content of the science of mathematics in a uniform manner and develop it in such a way that, at the same time, the interconnections between the individual propositions and facts become clear. The formula game that Brouwer so deprecates has, besides its mathematical value, an important general philosophical significance. For this formula game is carried out according to certain definite rules, in which the technique of our thinking is expressed. These rules form a closed system that can be discovered and definitively stated. Thus Hilbert is insisting that mathematics is not an arbitrary game with arbitrary rules, rather it must agree with how our thinking, and then our speaking and writing, proceeds. We are not speaking here of arbitrariness in any sense. Mathematics is not like a game, whose tasks are determined by arbitrarily stipulated rules. Rather, it is a conceptual system possessing internal necessity that can only be so, and by no means otherwise. The foundational philosophy of formalism, as exemplified by David Hilbert, is a response to the paradoxes of set theory, and is based on formal logic. Virtually all mathematical theorems today can be formulated as theorems of set theory. The truth of a mathematical statement, in this view, is represented by the fact that the statement can be derived from the axioms of set theory using the rules of formal logic. Merely the use of formalism alone does not explain several issues: why we should use the axioms we do, and not some others; why we should employ the logical rules we do, and not some others; why do true mathematical statements, e.g., the laws of arithmetic, appear to be true, and so on. Hermann Weyl would ask these very questions of Hilbert. What truth or objectivity can be ascribed to this theoretic construction of the world, which presses far beyond the given, is a profound philosophical problem. It is closely connected with the further question, what impels us to take as a basis precisely the particular axiom system developed by Hilbert? Consistency is indeed necessary but not a sufficient condition. For the time being we probably cannot answer this question. In some cases these questions may be sufficiently answered through the study of formal theories, in disciplines such as reverse mathematics, and computational complexity theory. As noted by Weyl, formal logical systems also run the risk of inconsistency. In P&O arithmetic, this arguably has already been settled with several proofs of consistency, but there is debate over whether or not they are sufficiently finitary to be meaningful. Gödel's second incompleteness theorem establishes that logical systems of arithmetic can never contain a valid proof of their own consistency. What Hilbert wanted to do was prove a logical system S was consistent, based on principles P, that only made up a small part of S, but Gödel proved that the principles P could not even prove P to be consistent, let alone S. Intuitionism. Intuitionists, such as L. E. J. Brouwer, 1882–1966, hold that mathematics is a creation of the human mind. Numbers, like fairy tale characters, are merely mental entities, which would not exist if there were never any human minds to think about them. The foundational philosophy of intuitionism or constructivism, as exemplified in the extreme by Brouwer, and more coherently by Stephen Klein, requires proofs. To be constructive in nature, the existence of an object must be demonstrated rather than inferred from a demonstration of the impossibility of its non-existence. For example, as a consequence of this, the form of proof known as reductio ad absurdum is suspect. Some modern theories in the philosophy of mathematics deny the existence of foundations in the original sense. Some theories tend to focus on mathematical practice, and aim to describe and analyze the actual working of mathematicians as a social group. Others try to create a cognitive science of mathematics, focusing on human cognition as the origin of the reliability of mathematics when applied to the real world. These theories would propose to find foundations only in human thought, not in any objective outside construct. The matter remains controversial. Logicism. Logicism is one of the schools of thought in the philosophy of mathematics, putting forth a theory that mathematics is an extension of logic, and therefore some, or all mathematics is reducible to logic. Bertrand Russell and Alfred North Whitehead championed this theory, fathered by Gottlob Frege. Set theoretical Platonism. Many researchers in axiomatic set theory have subscribed to what is known as set theoretical Platonism, exemplified by mathematician Kurt Gödel. Several set theorists followed this approach, and actively searched for possible axioms that may be considered as true for heuristic reasons, and that would decide the continuum hypothesis. Many large cardinal axioms were studied, but the continuum hypothesis remained independent from them. Other types of axioms were considered, but none of them has as yet reached consensus as a solution to the continuum problem. Indispensability argument for realism. This argument by Willard Quine and Hilary Putnam says, in Putnam's shorter words, quantification over mathematical entities is indispensable for science, therefore we should accept such quantification, but this commits us to accepting the existence of the mathematical entities in question. However, Putnam was not a Platonist. Rough and ready realism. Few mathematicians are typically concerned on a daily, working basis over logicism, formalism, or any other philosophical position. Instead, their primary concern is that the mathematical enterprise, as a whole, always remains productive. Typically, they see this as ensured by remaining open-minded, practical and busy, as potentially threatened by becoming overly ideological, fanatically reductionistic or lazy. Such a view was expressed by the Physics Nobel Prize laureate Richard Feynman. People say to me, "Are you looking for the ultimate laws of physics?" No, I'm not. If it turns out there is a simple ultimate law which explains everything, so be it. That would be very nice to discover. If it turns out it's like an onion with millions of layers, then that's the way it is. But either way, there's nature and she's going to come out the way she is. So therefore, when we go to investigate, we shouldn't pre-decide what it is we're looking for only to find out more about it. Now you ask, why do you try to find out more about it? If you began your investigation to get an answer to some deep philosophical question, you may be wrong. It may be that you can't get an answer to that particular question just by finding out more about the character of nature. But that's not my interest in science. My interest in science is to simply find out about the world, and the more I find out, the better it is. I like to find out. Philosophers, incidentally, say a great deal about what is absolutely necessary for science, and it is always, so far as one can see, rather naive, and probably wrong. The insights of philosophers have occasionally benefited physicists, but generally in a negative fashion, by protecting them from the preconceptions of other philosophers. Without some guidance from our preconceptions, one could do nothing at all. It is just that philosophical principles have not generally provided us with the right preconceptions. Physicists do of course carry around with them a working philosophy. For most of us, it is a rough and ready realism, a belief in the objective reality of the ingredients of our scientific theories. But this has been learned through the experience of scientific research, and rarely from the teachings of philosophers. We should not expect the philosophy of science to provide today's scientists with any useful guidance about how to go about their work, or about what they are likely to find. After a few years' infatuation with philosophy, as an undergraduate I became disenchanted. The insights of the philosophers I studied seemed murky and inconsequential compared with the dazzling successes of physics and mathematics. From time to time since then I have tried to read current work on the philosophy of science. Some of it I found to be written in a jargon so impenetrable that I can only think that it aimed at impressing those who confound obscurity with profundity. But only rarely did it seem to me to have anything to do with the work of science, as I knew it. I am not alone in this. I know of no one who has participated actively in the advance of physics, in the post-war period, whose research has been significantly helped by the work of philosophers. I raised in the previous chapter the problem of what Wigner calls the unreasonable effectiveness of mathematics. Here I want to take up another equally puzzling phenomenon, the unreasonable ineffectiveness of philosophy. Even where philosophical doctrines have in the past been useful to scientists, they have generally lingered on too long, becoming of more harm than ever they were of use. He believed that any undecidability in mathematics, such as the continuum hypothesis, could be potentially resolved despite the incompleteness theorem, by finding suitable further axioms to add to set theory. Philosophical consequences of the completeness theorem. The completeness theorem establishes an equivalence in first-order logic between the formal provability of a formula and its truth in all possible models. Precisely, for any consistent first-order theory it gives an explicit construction of a model described by the theory, and this model will be countable if the language of the theory is countable. However, this explicit construction is not algorithmic. It is based on an iterative process of completion of the theory, where each step of the iteration consists in adding a formula to the axioms, if it keeps the theory consistent, but this consistency question is only semi-decidable. An algorithm is available to find any contradiction, but if there is none, this consistency fact can remain unprovable. This can be seen as a giving a sort of justification to the Platonist view, that the objects of our mathematical theories are real. More precisely, it shows that the mere assumption of the existence of the set of natural numbers, as a totality, an actual infinity, suffices to imply the existence of a model, the world of objects. Of any consistent theory, however, several difficulties remain. For any consistent theory, this usually does not give just one world of objects, but an infinity of possible worlds that the theory might equally describe, with a possible diversity of truths between them. In the case of set theory, None of the models obtained by this construction resemble the intended model, as they are countable, while set theory intends to describe uncountable infinities. Similar remarks can be made in many other cases. For example, with theories that include arithmetic, such constructions generally give models that include non-standard numbers, unless the construction method was specifically designed to avoid them. As it gives models to all consistent theories without distinction, it gives no reason to accept or reject any axiom as long as the theory remains consistent, but regards all consistent axiomatic theories as referring to equally existing worlds. It gives no indication on which axiomatic system should be preferred as a foundation of mathematics. As claims of consistency are usually unprovable, they remain a matter of belief, or non-rigorous kinds of justifications. Hence the existence of models, as given by the completeness theorem, needs in fact two philosophical assumptions: the actual infinity of natural numbers, and the consistency of the theory. Another consequence of the completeness theorem is that it justifies the conception of infinitesimals as actual infinitely small non-zero quantities, based on the existence of non-standard models as equally illegitimate to standard ones. This idea was formalized by Abraham Robinson into the theory of non-standard analysis. However, this theory did not look so simple and did not have much success. More paradoxes. 1920, Thoralf's column corrected Lowenheim's proof of what is now called the downward Lowenheim's column theorem, leading to Scullom's paradox discussed in 1922, the existence of countable models of ZF, making infinite cardinalities a relative property. 1922, proof by Abraham Frangel that the axiom of choice cannot be proved from the axioms of Zermelo's set theory with U elements. 1927, Werner Heisenberg published The Uncertainty Principle of Quantum Mechanics. 1931, publication of Gödel's incompleteness theorems, showing that essential aspects of Hilbert's program could not be attained. It showed how to construct, for any sufficiently powerful and consistent recursively axiomatizable system, such as necessary to axiomatize the elementary theory of arithmetic on the infinite set of natural numbers, a statement that formally expresses its own unprovability, which he then proved equivalent to the claim of consistency of the theory, so that, assuming the consistency as true, the system is not powerful enough for proving its own consistency, let alone that a simpler system could do the job. It thus became clear that the notion of mathematical truth cannot be completely determined and reduced to a purely formal system, as envisaged in Hilbert's program. This dealt a final blow to the heart of Hilbert's program, the hope that consistency could be established by finitistic means. It was never made clear exactly what axioms were the finitistic ones, but whatever axiomatic system was being referred to, it was a weaker system than the system whose consistency it was supposed to prove. 1935, publication of the article by Albert Einstein, Boris Podolsky, and Nathan Rosen arguing that quantum mechanics was incomplete, as its formalism was non-local, which the authors assumed to not possibly reflect some true underlying mechanism that remained to be discovered. 1936, Alfred Tarski proved his truth undefinability theorem. 1936, Alan Turing proved that a general algorithm to solve the halting problem for all possible program input pairs cannot exist. 1938, Gödel proved the consistency of the axiom of choice and of the generalized continuum hypothesis. 1936-1937, Alonzo Church and Alan Turing, respectively, published independent papers showing that a general solution to the Entscheidungs problem is impossible. The universal validity of statements in first-order logic is not decidable, it is only semi-decidable as given by the completeness theorem. 1955, Pyotr Novikov showed that there exists a finitely presented group G such that the word problem for G is undecidable. 1963, Paul Cohen showed that the continuum hypothesis is unprovable from ZFC. Cohen's proof developed the method of forcing, which is now an important tool for establishing independence results in set theory. 1964, John Stuart Bell published his Inequalities, showing that the predictions of quantum mechanics in the EPR thought experiment are significantly different from the predictions of a particular class of hidden variable theories, the local hidden variable theories. Inspired by the fundamental randomness in physics, Gregory Chaitin starts publishing results on algorithmic information theory, measuring incompleteness, and randomness in mathematics. 1966, Paul Cohen showed that the axiom of choice is unprovable in ZF even without UR elements. 1970, Hilbert's 10th problem is proven unsolvable. There is no recursive solution to decide whether a Diophantine equation, multivariable polynomial equation, has a solution in integers. 1971, Suslin's problem is proven to be independent from ZFC. Partial resolution of the crisis. Starting in 1935, the Bourbaki group of French mathematicians started publishing a series of books to formalize many areas of mathematics on the new foundation of set theory. The intuitionistic school did not attract many adherents among working mathematicians due to difficulties of constructive mathematics. We may consider that Hilbert's program has been partially completed, so that the crisis is essentially resolved, satisfying ourselves with lower requirements than Hilbert's original ambitions. His ambitions were expressed in a time when nothing was clear. We did not know if mathematics could have a rigorous foundation at all. Now we can say that mathematics has a clear and satisfying foundation made of set theory and model theory. Set theory and model theory are clearly defined, and the right foundation for each other. There are many possible variants of set theory which differ in consistency strength, where stronger versions, postulating higher types of infinities, contain formal proofs of the consistency of weaker versions, but none contains a formal proof of its own consistency. Thus the only thing we don't have is a formal proof of consistency of whatever version of set theory we may prefer, such as ZF. In practice, most mathematicians either do not work from axiomatic systems, or if they do not doubt the consistency of ZFC, generally their preferred axiomatic system. In most of mathematics as it is practiced, the incompleteness and paradoxes of the underlying formal theories never played a role anyway, and in those branches in which they do, or whose formalization attempts would run the risk of forming inconsistent theories, such as logic and category theory, they may be treated carefully. Toward the middle of the 20th century it turned out that set theory, ZFC, or otherwise, was inadequate as a foundation for some of the emerging new fields, such as homological algebra, and category theory was proposed as an alternative foundation by Samuel Eilenberg and others.